we're talking about the calculator. Here's the adder. I got a display module. You need a debounce. Okay, so you have to plan for all the ports before you start working on it, right? Input, outputs. For any digital system, you have to design, right? And we can start from the smaller ones. There are so many different ports. That's getting people overwhelmed really easily and quickly. So, but we just look at the display module, for example. What we want to see on the display. So there's the IPGA, right? You got all the LEDs, and here's a 7-segment display. So it's just a one digit as a number. Another one is a sign. This is for sign. Okay, it's a sign bit. It's either nothing or a minus sign in front of it. Okay, depending on the 2's complement number. And it's a 3-bit number system. You have switches, 1, 2, 3, and 1, 2, 3. And so for the final result, remember we have the full adder. I'm not drawing the details, but you have the full adder, 3 bits. And the C final is being processed and eventually give you a, no, C2 is being processed, eventually give you a C final, C2 final. And here's S2, here's S1, here's S0. So you can see the final results is actually 4 bits. So you need 4 LEDs. 1, 2, 3, 4. 4 LEDs. So it's asking you guys to display this final 4-bit result at the LED, but also over here. So you can imagine if you have this 4-bit binary number available to convert it into a 7-segment display module, you only need a 1 block of code. And what is that? The decoder, right? Or the case statement. Remember the case statement. If you see this, you do this, right? If you see a different number, for example, over here is case, right? Let's say data. Okay, for the cases. If I give you 1, 0, could you let me know the format? How many bits? How many bits over here? 4. So 4 prime binary. 1, 0, 1, 0. Okay. In this case, I want to give sag a what? So this is what? This is minus 6, right? So sag should output a, so this is final output over here. It's 1 digit, right? So you want to display a what over here? 6. So it's the pattern should display it. It's a G to A and should be a 6, right? Should be a 6. All right. But the thing is, this is not 6. This is minus 6. All right. So the reason that you know this is minus number, is a negative number, is because you have a 1 as an MSB over here. 1 is MSB. So you want to display a minus sign in front of it. Okay. So when I'm talking through this, you know that this is English, but you translate it into Verilog, it sounds like a if data digit 3, right, is a 1, it's pseudocode, is a 1, and also when an what? an1 is 0 or 1 to turn it on. 0. So this is 0, this has to be 1. So let's just use two digits for AN. AN, if we define AN as 2 bits, so AN is 2 digit binary number 0, 1, right? If AN is 2 digit binary number 0, 1, which means this is on, this is off, and I'm gonna give a minus sign to this guy, right? But this digit should always display a 6 over here. That's a general picture of it. So we just need 4 bits, then we can display a number over here for the 7-segment display. So for the display module, it receives that data, which is 4 bits, and then convert it into this 7-segment displays pattern, right? And interface with IPGA's SAG ports. That's one thing. What else do we need for the display? It's not a unique answer, right? So we have multiple options for it. So the adder is the one we do the additions. Remember, we have all these. So the adder module handles the structure over here and outputs data for you. That's a 4-bit result. That makes sense, right? It's 4-bit result. What are the inputs for adder? Switches. So we need 6 inputs. Let's see if I can name it. Gave them a name. And just call them A and B's. And eventually these ones are being processed a little bit, and then they're being shorted to switches. It's going to be 5 to 0. I need a clock. Okay, we like to use clocks to synchronize everything. Need a clock. What else do we need for the adders? The adders takes the input, which makes sense. It takes the input and process it and edit it or do the subtractions, and also has a clock to synchronize everything. What else do we need for the adder, you think? C-1, remember this guy? I just call it CM1. So the carry in, overall carry in here, it should be a switch. Should be a switch. When you switch this on, remember we have this guy connect to the XOR gates, right? Have a 0, 1 to define the adder to be a subtractor or adder. So you have to add a CM1. So CM1 has to be a port because it's the input. You switch it on, it becomes a subtractor. You switch it off, it becomes the adder. So we definitely need a 1 here. It could be switch, let's say 15. What else do we need for the adder? That's probably everything, right? Oh, another bit I want you guys to display is over here. For the 5th bit from the right hand side, this should be the overflow bit. If it overflows, this one should be on. So in that case, the adder, so the adder's overflow bit, we know that OV equals C1 XOR C2. This is what we got from from Tuesday, right? So we definitely know that the adder will be able to output OV, so we don't have to output it to any other modules. We directly output it. So here is OV, and I just connect it to LED. It's gonna be 0, 1, 2, 3, 4, right? 4. OV, overflow indicator. And that's it. That's all the ports for the adder. For task, I think the first couple of tasks, without involving the serial in parallel out module, right? So we don't need a debounce for the first one, just to make it work, right? So we need the adder, we got switches, we got a C-, and we short it to the display, and the display shorted to here, and display need ANs as well, right? You need ANs. That's 3 to 0, even though you only need 2 bits because only these 2 bits are being used for the display. But you can claim all of the 4 bits. So, and the DP, right? DP is not being used, we just turn it off permanently. And I think that's it. So it takes in the data, 4 bits, and convert it using the lookup table or the case statement, convert it into the 7 segment display, and also you do a little control of the ANs depending on the data, right? Because, like I said, if you see the AN, you have to have an if statement with the AND logic in there, right? So the data, the MSB is 1, and this is the second display module is activated, then you just show a minus sign over there. You have more cases, but we'll type it up together really quick. So this is the big picture of the first, I think, at least the task 1 and 2, right? So for the one doesn't have a serial in, parallel out, so you have to give the data using parallel input. So parallel input is fine, it's just taking a lot of pin resources. So the parallel inputs, you can see you have to give the 6 switches inputs at the same time. So the modern computers have 64 bits, right? So there's no way that they can give a parallel inputs using 64 bits. And it's just for one of the numbers. The 2 numbers is going to be 128 switches. It's going to take a lot of time to put the numbers in. So it has to be serial input, right? That's why we do a serial in, parallel out. So you just need a one switch as a clock and another switch as a input. Just one pin input, serial input. So that's task 2 and 3. So for task 1, I think just for this guy, I think we did. Which one did we do? We haven't done too many yet, right? We just did the serial in, parallel out. We haven't done the display and the adder yet. Let's do the adder really quick. I wouldn't show you everything, but definitely a template will be provided to you guys, so you can start with that one. Now you see the big picture of the adders module, right? You can definitely start the module really quickly, effortlessly. Save this guy anywhere. Save it as the desktop. I'll do lab. Is that lab 4, lab 5? Lab 5 probably. W. It should be adder. Adder.v. So the desktop. And change the font size. Set UI font equals. And do a 25 over here. Make it big. Alright, definitely module. Set. Adder. See, what are the ports we have? So no brainer, at least the clock. Okay, clock. CM1, C minus 1, the carry in, overall carry in. A's and B's, right? A's and B's. What else? Data. We need the data, which is a 4-bit output, and we need the overflow indicator, which is OB. And clock is the input, CM1 is the input. They are both 1-bit inputs. And A's and B's are outputs, inputs, but multiple bits. So let's do this. A's and B's, and output. Because we expect that the overflow indicator will be assigned inside the always block, and it's on the left-hand side of the procedural assignment or the non-blocking assignment. So usually they prefer, I mean, just syntax-wise, there's no reason why, but the Verilog, the syntax is they prefer reg, a register type. So whenever you have a variable on the left-hand side of the procedural assignment within the always block, you need a register type. So let's do OV register type as an indicator, and the data as well. Data has 4 bits, so 3 to 0. Data. So these are all the ports we need by looking at the diagram. So the ports are not switches yet because it's a sub module, right? It's a sub module. It's not an overall top module yet. Now I do always. Because we are coding up the structure of the adder. So you have to, it cannot be just the top level of the boxes. It has to be include the details of the full adder. If we go back to the schematic of the full adder, let's just do a quick review on it. I'm not going to go through the details, but just for the schematic of it, right? What do we have over here? So we know what are the ports we need. CM1 is the overall input. CM1. This is C0, C1, C2, S2, S1, S0, and we have A, B, A0, A1, A2, B2 directly get in there, B1, B0, and this guy has an XOR gate over here for the 2's complement. And another pin is shorted to the CM1. I have a switch. Okay, so that's the structure here. So we need to write down the logic for the full adder, definitely, and we know that the full adder's S equals what? A XOR B XOR carry in, right? That's for the first stage. That's given. That's from logic. I don't want to derive it for you guys, but this is given. Consider this is given. Okay. And for C out, for C0 or C out for the first stage, for the following stages it's gonna be the same. But for this stage, this equals A0 or B0 and the CM1 or A0 B0. I think
it's backwards. It's A and B or C and B XOR A XOR B. So
let me check real quick. A and B. Oh, A and B or A or B and this one. So you are saying this can be XOR?
No.
Yeah, there are multiple. There are 2 ways to for CL. I think this is a better option because this got rid of the static hazard. I think you have a different option here. You can have I forgot the other option since I rarely use it. But this one works. This one works. Right? I'm teaching logic. I'm going to derive everything for you guys, but don't have the time. So let's just keep using this one. There's another option. I think they used. I think they changed one of the signs, and it also works. But that one involves a static hazard. So this is good. And we need a logic to figure this out as well. Eventually, if we put everything in the always block, the signal lines like these ones are not ports. They're not ports, but they need to be a reg. They need to be a register type because I'm assigning something to it, right? In the procedural assignment, in the OS block. So they all need to be register type. I'm gonna do that later. So I'm gonna start just using it, assume I have it, and then I'm gonna declare it at a later time. Is that fair? That makes things easier. Okay. So I'll just declare it when needed. Let's do always. Pause edge clock. So it's just adder. It's not supposed to do anything else. It's just do adding or subtracting, right? Depending on the input. So for the as, you have a very definitive answer because all the as, we already have the logic expression over there, right? So we can define what. So as has 3 bits, right? So as will not be ports, and there will be a register type because we don't need an as to be ports, and because we need the data to be the final output. Does that make sense? So see here, data is the output, but as are not the output. So eventually you are expecting something like concatenation C2 final, as2, as1, as0. Assign it to data, so data becomes the port. These are not. So you are adding a intermediate layer over here. You connect all the C2 finals and as, or the summations, to the left-hand side of the different flops or the registers, because this assignment does that job for you, right? This is like a different flop, parallel in, parallel out, latches. Okay, so these are not ports, but this will be the final port, which is data, called data. Okay, we assign this, we do a concatenation, we assign it to data. So in that case, these are, so for all these ones, these are not ports, these are just registers, because they're on the left hand side. Okay, and we can do a register type. Let's do as first. So as would be, sorry, how many bits? 3. Makes sense, right? I'm gonna do uppercase S, register type. What about C2? C2 is just a carry out over here. And do we expect any assignment, any assigning to C2? Of course, because if you need a C2, you have to do this, right? With A2, B2 over here, and C1 over here, and then A2, B2, then C2. So C2 has to be a register type as well. Do a C2. What about C1? Same thing, same concept. So intermediate register. C0, same concept. But C minus 1 is a port. But C0, C1, C2 are not ports. Anything else we need for this? Let's just keep it as is right now. Then we'll add if we need more. So we are trying to do a as, right? As 0. What is as 0? We find that, oops, so A0, A1, A2s are not directly assigned to the inputs of the adders. There's an actual gate. So what can we do? You need another variable over here. Even though you don't see anything, but to implement into the IPGA, you need a register type as intermediate data over here, because you are having the C-1 and A2 being XORed, and eventually you assign it to another one. You need to hold the value over here. So you need a name for this net. Okay, if this is considered as a net, you need a name for it. You need a name for it. So we find that, hey, we need a name for that net. So let's just call it AA instead. We may have a better name for it, but 20 AA. All right. So in that case, we find that, hey, I couldn't directly use A, so I have to figure out AA first. So AA 0 is what? A 0, X or what?
X would be 0.
AA0 is this line, is this net over here. AA0, right? So AA0 is A0, X or what? X or CM1, remember? You X or the carry in. If it's a 1, it flips all the A's for the 2's complement. If it's a 0, A X or 0 is not changing it. So the drawing here is not very good. Let me make it clear. So for the top, yeah, I was thinking you can remember it, but it's not the case. So the B2, A2, B1, A1, B0, A0. That's one port of the XOR gate. You connect to all the A's, and the second port are being shorted together. And eventually, it's being shorted to CM1. And that one is controlled by a switch. You can have an option to be 0 or 1. And the reason for that is, if you want to use a subtractor, for example, B2, B1, B0, plus minus A2, A1, A0, this becomes a subtraction. We need to convert all the A's into its 2's complement counterpart. And the way to do that is, because 2's, by definition, 2's complement, the negative counterpart is you flip every single bit and add a 1 to it. Okay? So in order to do that, you have all the A's here. So now we want to flip every single bit and add a 1 to it. How do we do that? You do A2, A1, A0. For every single bit, you XOR it with 1, right? If you XOR it with 1, because we know that 1 XOR 1 is going to be 0, 1 XOR 0 is going to be 1. So if we consider this part is A, so A could be 0 or 1, doesn't matter, it's the case, right? So if you use A XOR 1, or anything XOR 1, it's going to be A naught. See? A naught, A naught. Since it's being XORed with 1. So if you XOR 1, you're getting A naught. Alright? So in that case, we want to flip all the A's. We need to XOR all the A's with a 1. That's why we put an XOR gate over here, and we switch it to 1 for C minus 1. So switch to 1 for this line. This line is providing an input to the XOR gate and also adding a 1 to C minus 1. So it's basically doing a flipping every single bit, bitwise, and then adding a 1 to it at the same time by switching this line to 1. That's why we are doing this. So these nets are called AAs. We just name it AAs. Okay, that's the structure. So my question for you here is come back to the code, right? So this should be AA0. It's going to be A0 XOR what? CM1. It's a port, depending on the CM1's value, which is controlled by a switch. Do we have a CM1 net? Yes, it's a port. You can directly use it. Alright? Same concept. That's why you want to use Vim, right? YYP, YYP, right? And R replace, R replace, R replace, R replace. So for AA1, it should act for what? AA1, by looking at this AA1, here's AA1, right? X or what? Oh no, sorry. AA1 is A1 X or what? CM1 still, it's not changing. Because whenever you want to use a subtraction mode, every single bit need to be flipped. So you shouldn't change this one as well. Same concept. Yes, you are just keep adding to it, right? You cannot finish everything at a time. So now we got all the A's. We got all the A's. Why we need A's? We have to come back to the original design. Why we need all the A's? Because we want to get S. So now let's come back to S0. S0 is gonna be what? What? AA0. See? AA0, XOR B0, XOR CM1, right? It's gonna be S0. XOR B0, XOR CM1. YYP, YYP. Replace, replace. Replace, 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 replace. But this need to be changed. For S1, this has to be what? C0, and C0 is C0 available? Did you declare it? Yes, 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 we do, right? Change all these accordingly, so you can directly see it on the diagram. So that's why you want to always draw the diagram, draw all the intermediate signal nets or ports physically, so you can, when you're coding it up, you can look at it, right? So this is basically a hardware description. So you don't want to, on a resume, you don't want to put Verilog as a software skills. It's not a software. Okay, it's hardware modeling. It's coding, but it's not software. What else? You got A's, you got S. So you are basically using some signals that you don't have. You have CM1, but do you have C0? You don't. You don't have C0 yet. What is C0? Yeah, it's the output, right? It's the intermediate carry out. But the thing is, you just declare as a register type, there are going to be zeros as initial value. And however, you guys all know that this, if you use a non-blocking, right, it should be non-blocking. Non-blocking. It's a hardware, it's a snapshot, right? So all the signals from the right-hand side will go to the left whenever the clock rising edge arrives. So in that case, when the first clock rising edge arrives, you don't have any C0 and C1s, right? You don't have them. They are just zeros. After declaring as register, they are holding the initial 0 over there. So even though it doesn't matter that much, because eventually it will be updated at the later clock cycles, but it's still better practice, you know, to have the signal ready. So you do need C0, and you need a C1, right? You need a C2. Yep, you need a C2. You C2. And these inputs are fine because A's and B's are from the switches, right? If you give us values to the switch, including CM1 as well. So they are available at the port. But the C's are not. So you have to get the C's first, right? So according to the equation over here, you can definitely, because all the A's and CM1s, all these are inputs, so you can definitely use it. So what is C0? Yes, AA. Good. AA what? C0 is AA0. I use the AND. I can use OR, right? OR. So let's do an OR for it. According to the logic expression, OR B0 first, and parentheses, and this guy AND with CM1, and the whole thing is ORed with A and B, right? So it's gonna be AA, sorry, AA0 and B0. Just in case we add a parenthesis to it, make it more readable, and also make sure we are not making any mistakes over here.
Seems like
It might be fine, right? Might be fine. Like this. Right? I think this is right by far. And now I find out that I shouldn't have these ones here at the very beginning, since I can do a YYP, right? I like that better. Replace. And this will be one, or the ones, do a replace. So, because the first line does the C0, so I can use C0, even though it's a procedural, and it doesn't really matter because the right hand side goes to the left at the same time, but at least the next cycle C0 becomes available, it's going to be updated, right? So you'll probably get some incorrect intermediate values, but the clock is running at 100 megahertz, it's updating so fast. Even though you got a one incorrect value somewhere at some time, and the next clock cycle will definitely update it, and you won't be able to see it, right? You won't be able to see it. All right. I think we are done with the major ones. What else? Okay, so the logic, right? The logic we did. Remember the OV is what? OV? You can just look at your notes. I don't have to give a hard time on that. So let's just say it. OV. OV is, it's gonna be C1 X or C2. We did it last lecture. And also, overflow?
that's what I have in my notes.
No, it should be C1. It should be C1, C2. XOR logic. Yeah. C1 XOR C2 to find out overflow indicator. And for C, we also need a C2 final. Right, C2 final. That's the final C2 you want to use as a MSB for your final result, because if it's overflow, you want to use the actual carryout. If it's not overflow, you want to duplicate MSB or S2, right? So you have to take care of that, and that logic was already processed. You don't have to handle this kind of English logic anymore because it's already carried out by the truth table and already being converted into a logic expression. Right? That's the benefit of using logic, because we already put all the variables and considerations in the truth table, and we derive all the logic expressions from the truth table. Then we don't have to go back and think about the English logic anymore. It's directly already involved or included into the logic expression, which is the C2 finals logic expression right here. We did on Tuesday. You can watch the lecture video to find out the answer. I'll just type it over here. That is overflow not ended. Wait. You end that with a as tool and you OR this with OV and not as tool and C tool. I may have some typos in the examples. If it doesn't run, it's gonna be a good chance for you guys to debug it. It's gonna train your debug skills. No matter what, it's gonna be good, right? It's either let you guys code up everything from scratch or work on some debugging skills. All right. I don't see any other things I need over here.
Do we need to add C2 final at the top as a register?
Oh yeah, that's right. Good point. Thanks. That's good. Yep. What else? Cool. What else? Start a new line. Below it is what? Lowercase o, right? And the module. Okay, so this is for the adder module. I already did it for you as example. And for the next one, I think I will just do most of it, but instead of everything. So by looking at the diagram, system diagram over here, what else do we need to complete it, or what else we haven't done yet? Let's do display. Okay, let's do display. Because the first and second examples doesn't involve any of the debunks and serial in parallel modules, so it's gonna be display. You just need an adder and display on top. So I definitely won't code up the top for you. It's so simple. So let's work on display.
What's the order of operations for C2 final? That wasn't like which and or goes before the others.
Which and the ors go to the others.
To go back to the code.
Yeah.
Like that, you know.
Uh huh.
That's just gonna go left to right.
Left to right. Right to left, right?
Huh? Is that correct?
What do you mean by left to right?
That's how it's gonna like
Right to left.
put those. Is it right to left?
Yeah.
Oh, okay. Well, it's one of the two, but is that gonna be right? Is it gonna and not S2 and C2?
Hmm.
Or V and then or?
Oh, you mean for the?
And like, should there be more parentheses?
Yeah. Let's try this.
Okay.
Yeah, I think this is the original intention here. This will guarantee that this works, right? But I didn't include the parentheses over here, and it worked. It worked. So this is more readable, definitely. Okay. It's more readable. I wonder why it worked. I think we should add a parenthesis over there actually, but it worked.
What about on the left side?
On the left side, the left side is done because it goes from left to right, right? That's why it should be fine.
Okay, so it does go from left to right.
It should, yeah. But why the second one works, right? That's the question. Yeah. Yeah, anyway, but add the parentheses will make it clear. Definitely. Alright, okay, let's do display one. Display one. How do we start a new window over here? VSP. Vertical split. I don't know what P is. Huh? Just a name.
it's just-
I'll just do it. I mean, usually I'll just do it. It duplicates it, but wait, duplicates it. I forgot. It shouldn't duplicate it.
I think it's just the same.
Yeah, it's a duplicate. So what I'm gonna do is, I will.
It's the same file.
It's the same. No, it's not. It's not. See, I could save this as display.v, right? Save it as display.v. I don't know. I forgot. Oh, it's the same file.
I don't know. I think it
Because they are
is.
both display.v.
I think. Well, yeah, unless you save it as something.
Let me see. Yeah, I think you need to add a name to it probably.
Yeah.
Yeah, change the name. Oh, but the adder is still here. See the adder? Adder is still here. Right? Yeah, see the parentheses over here?
Yeah.
That's what we did today. So this adder is still here. And I saved it as a display and become the display as an actual file. So we're good. Display. So let's come back here. I was expecting an empty file, but it's not. I hate it. Module disp. What else? Sag, an, data. Let's keep it as is right now. So input, clock, for sure. Input, data, 4 bits. Output, how many bits? Do we have to include all the bits over there? Probably not. Did I do that? Oh, because these are not IPGA modules, right? These are not IPGA modules, and you may need to change some of them into register type. But for now, let's. Usually, output should be registers if they are being included on the left-hand side of the procedural assignment in the always block. But for inputs, we usually don't do that. It's gonna report syntax errors. No reasons. It just the Verilog just doesn't like it. It's basic rules. Okay. So for output. Because these are not final ports for the IPGAs. These are just sub-modules, right? They're interfacing with the IPGA's ports. And 7 segment have 620, and it's a SAC. And same to AN, right? It's gonna be 320. And if we don't use all of them, let's just do 120. Let's just keep it light. It's gonna be fine. I mean, there are 4 bits, but we only use the first 2 digits. Let's don't use the 2 on the left hand side. So ANs are registers. What else? Data, clock, registers. You know, the decimal point is such a simple thing. We just do a very simple assignment to it. Just assign a 1, so we can turn it off. We don't have to worry about that. It's very simple. It's not being shifted, not being put in any concatenation. It's just very simple off, right?
Should that be in the module declaration?
Module declaration. Wait.
Right after display. The clock says AN data.
Uh-huh.
DP's not in there.
DP's not in there.
Yes, that's right. So it's a port, right? Mm-hmm. Okay. So the display module, since we have to control the counts, it switched back and forth between the 2 display modules. So we need a count. We need to count it. So in that case, we definitely need a parameter. Let's call it count max, and I don't know what that is, but let's just assuming this much. Hopefully, it's switching back and forth between the two units. It's a sweet number. It doesn't have to be this number. It could be 70,000, could be 100,000. I don't think that matters. But I think sometimes if you make it too fast, you are seeing a ghost digit over there. If you make it too slow, it blinks. So sometimes you find a sweet number, just stick to it. So this works for 2-digit display. And we also need register type. We have to count, right? We have to count to 65,000. I think I used the 16 bits. It's gonna be 15 to 0. That's gonna be enough. But you can do a conversion if you want. How many bits do you need, right? Then we do always. Yes. Begin and because this is a register, sorry. And this is a register, so I think we can give an initial value to it. So it starts with to display a number instead of displaying a sign, right? So AN, you can choose to start with something. So it's not zero, it's not starting with 0 zeros, right? You need to give an initial value. So only one is on, one is off. So in that case, we can assign initial value to it. If we do a 2-bit battery number, let's do 0, 1, for example. It doesn't matter because you are always flipping these 2 digits. And for DP, before we forget it, let's just assign something to DP, right? Just very simple static combinational logic. Just assign a 1-bit 1 to it, I think, right? So we can turn it off. 1. So it's off. So for always block, you could. So how do we plan for this one? I mean, remember one of the questions on the in-class module. I think I was asking you guys, hey, can we do multiple always blocks in one module? So the answer is yes. You just cannot include the same variables in both always blocks because there will be a conflict, right? Or you're driving the same net using the same clock. It's gonna be an issue. As long as you are not making that kind of mistake, you will be fine to have multiple modules, and you can separate the control of the different signals, right? So you can definitely have multiple ones. So for example, the first always block, we could do we could just switch the AN bits. How about that? Whenever the counter reaches the counter max, we flip the AN bits, so we switch to a different display. So it's activate this one or activate this one. Because no matter what, whenever the counter max is being reached, then we want to flip it, no matter what. Is that true? It should, right? It should be, because we are doing the counter max. We are either displaying over here or displaying over here. It's doing doing this. And since all the 4 digits are sharing the same data line, right? So, but now you are using 2 of them, but still they share the same data line. So you are just doing this and sending different signals to them. So if we just focus on that, it's gonna split the complex problem into multiple simple ones, and we just focus on that one because this is true. No matter what, they are being synchronized, and this is always true. So whenever the counter max is being reached, and remember we prefer to use this instead of using equal counter maxes. You may skip it. Actually, let's try to not have an indentation over there.
Why not use an extra, like, why not make just another module to flip and then call that?
A different module just to flip A, and I think you can, but why?
To,
So
seems like it would make the code more readable,
more readable.
right?
Yeah.
Like,
We can try it.
and more modular, you know,
Yeah,
then
like-
you can just use that module if you need
Yeah.
to do this again.
Yeah, I think like after this, let's try it, see what happens. I'm curious. So you can really interface with it. So if you include another module, then you need a ports, right? So what's gonna happen is because, but coming back here, so what's gonna happen if you have a different module?
You just take,
You still use the same clock, right? One clock reaches display, another clock reaches we call it flip AN or something, and that one just have an AN outputs being flipped. I think there's no difference.
yeah.
It's just like a separate module, but you take the AN ports from the display module to another module and just keep flipping. It's just do nothing but flipping the 2 bits. I think you can. Yeah, shouldn't be a problem at all.
Yeah.
Yeah. You know what I mean? So it's just to take this out, right, and then have two pins, input, output, and clock, right? Yeah, I think that works. All right. What should we do? No brainer, right? Whenever counter reaches counter max, reset the counter. You don't have to understand what's going on, but you need to know that I need to reset the counter. What else? What I'm doing here, I reset the counter, I need to flip AN. Are you allowed to flip AN? Yes, because the register, you can definitely do like flipping, shifting, whatever. How to flip it. I'll leave it to you guys, okay? Alright. Will that be difficult? You have initial value over here. If you have to flip it, then just, right? Swap it. Else. This will always be true. No matter what other modules you have. This is always true. It's a snapshot being implemented on the hardware in the IPGA. No matter what, it's always doing this. So that's why I just separate it from a different always block. Let's just do it here. Nothing will change it. Okay? And the counter is actually just serving the AN bits. It's just flipping the AN bits and nothing else. So I'm not expecting to use the counter in another OS block, which is causing conflicts. I'm not doing that. So the counter is only serving the AN. So I'll just do the counter and the AN over here in this OS block, then I'm done, right? What else we need to care about for this display? So now we have a controller is always running, like doing this, right? It's always doing this. So we need to use it, right? We need to use it. Let's use the same clock to synchronize it. And you don't have to always use the same clock. If you need a signal which is slower or faster, you can always do that, right? But now we just synchronize everything. It's a super simple example. And we know there's something is swapping like this all the time. And how do we use it? We need to catch it, right? So whenever it is this, we do this. Whenever it's that, we do that, right? So we need to catch it. Okay? So the thing is, whenever an equals, it's a 2-bit, right? It's a 2-bit. Equals what? Equals this, right? Equals this. What that means?
That means you're showing either nothing or a negative sign.
Yes, so which means the second digit is being activated. And now you want to put something over there depending on what? Depending on your result. From where? From where? So now I catches the moment that the second one is being activated. I want to either throw a negative sign over there or display nothing if it's a positive number. So I'm looking at which ones, which bit.
Looking at the MSB of data.
Yeah. Okay. So what else you want to put in here?
And if the data, yeah, data
Is equal to 1.
Okay, so if it's activated, if it is a negative number, stack, right? Remember it is G2, G2A, G2A.
Just like 0, 1, 1, 1, 1, 1.
Is G the middle bar?
I think it is.
Okay, cool. 7, right?
Yeah, it is.
Anything else we need to do within this block? I don't think so. So this is gonna be a display a negative sign over here. All right. Any other cases? Want to keep going, right? Because it could be a negative number, could be a positive number. So we want to do an else if. Else if this guy is still activating that bit. However, data, the MSB is a 0, right? And then it's just one-liner, so we don't have the begin and end actually. So we do a sag. It's gonna be a 7 digits and 01s, right? So it's a positive number.
Don't you not need that second condition on that one? Like data 3 is equal to 0?
The second condition, what?
Because if the first condition
else
fails,
if-
data 3 has to be 0.
Like you won't
Oh,
ever
but
get
yeah, but you have more cases, right? You want to make it more specific, so it definitely enters that entry. I think. Just in case, it might work actually. Sometimes you have to think about, oh, it probably the rest covers all the conditions, the rest of conditions, but just in case, I mean, make it more specific, definitely enters it. And you have more conditions over here.
Yeah, but not if you limit your, like, you use the still AN, you still need AN
Yeah.
is equal to 2B01, but you don't need the data one.
What are you suggesting to change?
Just to remove data if 3 is equal to 0.
What about this one though?
That one you need still.
Yes.
Yeah.
So else if still this one, but it's
Not that one.
the rest.
Yeah.
Yeah, I'm not sure. You can try it. But this one works, right? You can try it. Delete this one, see if that works. Okay? Definitely. Else if it's covered all the cases for the second one being activated. So we want to see. Would that be would that be else always? Probably not. We could. Let's see. It could be else.
Only other case is just and is 1 0, right?
Mm-hmm. So I think there are two solutions to that. You can either just use else if you believe that's going to be cover all the rest of the cases, or if you're not sure what the rest of the cases are, you just keep using else if and never use else. Right? Let the hardware to decide, make the decision, see what happens. It's fine. Right? And that'd be perfect.
If you keep using else if.
You can, yeah. And
But if you do and you don't cover all of the cases, it'll error out.
That's right. Yeah.
Yeah, it doesn't like that.
Yeah, but do you have other cases? That's my question. That's a
That's
trade-off,
what I'm
right?
saying. If you put else if and it works, then you don't have other cases. But if you put else if, then there
Yeah.
are other cases, it's not gonna.
It's not gonna be covered, right?
synthesize, Yeah.
Yeah, yeah.
Because it's not a real thing. Like it doesn't exist.
That's right. It's a bug in the
Right.
code.
Yeah. Like you can't hotwire that.
Yeah. If you're designing a toy, it's fine. If you're designing something for the airplane, probably not. Airplane, you have to cover all the cases, make it super specific. It has to be else ifs, not else, right?
That's all the fun out of it.
That's the fun of it. It's not fun to write it.
Yeah, I think if you're not sure, you should put else.
Else, I don't care. Just do whatever I have to do.
Just dig in the sky.
Yeah. All right. So else if an. All right. So now it's one on the right hand side, and we don't care about the sign anymore, right? Do we? Do we care about the sign? How do we differentiate positive and negative numbers? How do we differentiate the positive
Most
and negative?
significant bit of
Hmm?
data. MSB.
Yeah, I know, but the thing is, now we have to do a. So in here, right in here, this has to be because now the one on the right hand side is activated. You are supposed to display data over there or pattern for SAG. Okay, that's the moment to display SAG. So it has to be a case statement, right? It has to be a case statement. And you are looking at data, right? Data. Before I forget. Let's say let's do a. What are the numbers we have? What are the ranges? It's gonna be on the quiz, okay? It's gonna be on the quiz on Tuesday. So what are the ranges? For 3-bit 2's complement, what are the ranges? Let's say you don't have to memorize the pattern or the equation, but you can always think about it. So that's the biggest two positive numbers you can add to each other. But the thing is, they won't be able to hold. There will be overflow, right? They won't be able to hold. But the 3-bit, 3 digits plus 3 is the largest you can display, you can handle, and this is the most negative number you can handle for 3 digits for 2's complement. So this is -4 and positive 3, right? Okay, so for the cases, can you display a -8 over there? No. Can you display? Wait, can you display -8? Can you display a -8?
I mean, yeah.
Yes, since you have 4 digits for data, right? The port has four pins, isn't it?
Would it just be 1 0 0 0?
Yeah. See? 1 0 0 0. So your adder or subtractor should be able to handle that. Because the customer probably will put a -4 plus -4, or I don't know how that works, but the thing is, it should be able to handle all the numbers on the 4 digits. And if you have a 4 digits output, it should be able to show you all the possible numbers over here on the display, right? For example, if I put a 1 0 0 0 here, it should be able to display a -8. But is it possible to get a -8 as a result from the adder or subtractor? Probably not.
-4.
But how do you put a -4 for the B's? Since the B's doesn't have an actual gate, you're not flipping that.
Oh yeah, I guess so then.
Oh, you can, because if you put 1 0 0 will be -4. Right? Wait, is it?
Yeah.
Yeah, it should, right? It will. It will be -4, 1 0 0, and then 1 0 0, and you put this one to 0. Right? Should be a -4. Okay. So you do have -8, but just in case, we want to display all the numbers from 0 to 9. Okay? That's all the numbers you can have for 1 digit. So for all the cases, we could do a data is how many bits in data? 4, right? If I have this, everyone knows what that should be, right? The pattern, whatever, right? If I have this, we know it's a +1. What is +1? Let's see. It's a G2A, right? G2A. So it should be. Let's see. A, B, C, D, E, F. So E and F should be zeros. A, B, C, D, E, F. Right? And I assume this is +1. So what about -1? What's -1?
Isn't it just 1? Because then we have the sign bit.
But it's
Just a 1, right? Just a 1. It's gonna be 1. You just have to handle the sign over there. So the thing, what's the case for data in that case?
1 1 1 1.
So we got 2 different cases to show the same number, right? Same number. You just have to handle the sign in a different way.
Is there any way we can store those in like a parameter or something? Like, so that we don't have to type it out every time?
Yeah, so it could be the decoder sign module, right? The display is like a decoder. So you are saying you can just code the function somewhere directly, right?
No, I'm just saying like store it like a parameter or something, you know? Like just to have like, so that you could just type it in as if it's like a variable.
Yeah, I think the best way is that you do it. You just create a different module, because sometimes for this case, right, it's a different application. You have to swap these 2 bits all the time. It's a different operation being added to it. But the thing is, all these ones are never changed. You could just create a sub module and just call it decoder sub module and have the data as the inputs and have a SAC as outputs and just store it on a hard drive, and every time you need to use it, just burn it up and instantiate it in the top module. That's the best way. But for here, since we haven't done that too much, I mean, we can just type it or copy it, paste it from somewhere else. So just want to show you, you'll do the rest, right? But for this one, +1, and -1, you need the same number here, right? So 1 0 0 1 1 1 1. If I'm right. Not guaranteed. The same concept for other numbers, right? The positive number, negative number should be the same. 7-segment display output. Am I missing anything here for the whole display module? I think that's a major template for everything. And we're still not getting to the debounce module yet. And I will cover a little bit about that on Tuesday. And so you guys will do the top. You do the top for this one, and do the top for the serial in parallel out one as well. They can work on the lab on Tuesday. So we'll do the LCD module and memory stuff as well on Tuesday. But I think this is good. So you guys are pretty much ready for the lab. Any question on this? It's very fun, right? It's very fun. I like it. And you guys are good. Exceptionally good. Capable. Problem solvers. And you are pretty new to this. These guys are seniors. You are pretty good. So new. Doing well. And if you like it and you are doing well, which means you are talented in this kind of task, right? You are talented. I couldn't imagine if I don't like it. For example, you should imagine, right? For example, now I force you to switch your major to biology or chemistry. Can you do it? You are capable of doing that, but you cannot do it, right? Since it's so boring to you. So that means you are talented in this topic. Just keep doing it. It's a gift. Couldn't imagine, it's a gift.